Hello students, so in this lecture we shall be discussing about exchange bias and exchange bias and magnetic anisotropy. Now, if you look into the elements or the transitional elements, then we can see that nickel, iron, and cobalt, they are the most important films for exchange bias. Most important magnetic films, if they are deposited in the form of films for uh, exchange bias. Now, the most technologically significant exchange bias materials have rock salt structure. Second point is that the most technologically significant exchange bias material have been the rock salt, have a rock salt structure. Uh, Now we know that in for an exchange bias we ought to have a ferromagnetic and an antiferromagnetic layer. So talking about the antiferromagnetic layer, oxides like nickel oxide, cobalt oxide, and rock salt intermetallics. Uh, like iron and manganese, then nickel, manganese, iridium, manganese, and their alloys have been used as the antiferromagnetic part. Now, exchange bias was discovered in 1956, and the first device was produced by IBM based upon this exchange bias phenomena. That was recording heads. Now, the magnetic anisotropy is, if we look into the other aspect of the magnetic materials used in exchange bias, then we need to understand what is the magnetic anisotropy is. So, magnetic anisotropy is basically we call the directional dependence of a material's magnetic property. Material's magnetic rational depends of the material's magnetic properties, and the magnetic moment of magnetic anisotropy materials tend to align with an easy axis. The magnetic moment of a magnetic anisotropy material they tend to align with an easy axis. They tend to align with an easy axis. Which is an energetically favorable direction of spontaneous magnetization. So what we mean by easy axis is the energetically favorable direction of spontaneous magnetization. Plot. So if we
जिन जिन ने मेरे लाला की मदद करी बाहर के भीतर जहाँ को जो भी कोई भाई की धन्यवाद मैं तहज्जुद.
So if we plot the magnetic moment which is ampere per meter square with respect to the magnetic field given in Tesla, so we get, and this we do for magnetite, so we get two different directions, two different plots or two different directions. So for the easy direction we get a plot like this. This is the 1 1 1 direction, which is the easy direction, and for the hard direction we get a plot like this. This is for say 1 0 0 is the hard direction. So if you look into the crystal structure, it is basically an FCC. It means This is how the structure is with atoms at the 6 faces. So this direction, this is supposed to be the 111 direction. This is the easy direction. This direction is the 100 direction. This is the hard direction, and you can also have a 111 direction, a 110 direction. This is a medium, neither easy nor hard. Now, another interesting fact about the magnetic anisotropy is the domain wall thickness depends on the anisotropy of the material. Domain wall thickness, it depends on the anisotropy of the material. And although it depends upon the anisotropy material, the average spans across around 100 and 150 atoms. So the domain wall, although it is depends on anisotropy material, it is spans upon 100 to 150 atoms. And the anisotropy energy is lowest when individual magnetic moments are aligned with the crystal lattice. So, anisotropy energy is lowest when the individual magnetic moments are aligned with the crystal lattice. And crystal lattice axis, thus reducing the width of the domain wall. Yes, and thus reducing the width of the domain wall. Now next we discuss a phenomena, it's called the deepening of a domain wall. Now, non-magnetic inclusions in ferromagnets or dislocation, crystallography structure cause spinning of the domain walls. So you can see that non-magnetic inclusions in ferromagnet or dislocations, they actually cause pinning of the domain wall. Pinning and to unpin it we require an external magnetic field to unpin it. So let us pictorially understand this.
बाबा सबसे अच्छा और कम झिकझिक में पर्सनल लोन कहाँ मिलेगा बेटा?
So we have a domain wall, say this is a domain wall separating two magnetic moments. In this case, magnetic moment is in this direction, and in this case is in this direction. However, if there is some impurity introduced in the domain wall, so what it will do, it will cause pinning. So to remove this, so now what will happen, the domain wall will be now not exactly like this, but it will move around this impurity. Now to remove this and to unpin the domain wall, we need to apply an external magnetic field. So what the external magnetic field will do, it will shift the domain wall such that it is no longer touching the impurity. So even though the impurity is present here, since the domain walls has shifted, so it is unpinned. So this act of unpinning will cause sudden movement of the domain wall. And a sudden change of the volume of the both neighboring domains, and also a change in volume of the neighboring domains. Next, we introduce the concept of a block wall. A block wall is when the magnetization rotates through the plane of the wall. You need to have the block wall. And we also have something called a kneel wall. Kneel wall is the wall which rotates within the plane. Now, orientation of the domains with spontaneous strain will also change by an applied stress field. So, orientation of the domains with spontaneous strain will also change by an applied stress field. And because of the mechanical anisotropy that elongates or contracts the samples in certain directions. This is due to because because of the mechanical anisotropy. That elongates or contracts the sample in certain directions. So the block walls are mainly important in the case of films. So you can see that block wall domains are mainly found in bulk materials, whereas the Neil wall domains are mainly found in thin films.